Welcome to the last part of this lecture. It's about water balance diagrams. The reason why people use water balance diagrams is that information on precipitation is sort of limits the discussion, because it's only the water that arrives at a surface. But there are more aspects to it, because you also have evaporation. The water is lost from a surface. Or you have evapotranspiration, can also be lost through the uptake through root systems of plants, or the evaporation from leaves. Okay, and then also it's about the soil, the capacity of soils to actually store water. So if you actually have fully saturated soils, then the evaporation can actually provide more moisture for the air over a longer time. So precipitation alone is not sufficient information if you're really interested in soil conditions. Okay, so what is a water balance diagram? Let's talk about this. So just defining the terms we're talking about. Precipitation is the freshwater gain across the surface due to rainfall. Again, we had that in the climographs. Precipitation is the rainfall that falls. Evaporation is the freshwater loss across the surface due to evaporation. Evaporation can happen at the same time as precipitation. Okay, one is a source, one is a sink of water. Transpiration, is the process of water movement through a plant and its evaporation from aerial parts such as leaves, stems, and flowers. And if you combine evaporation and transpiration, you get evapotranspiration, called ET. Combined water loss from E and T. The word what we also use is the term potential evaporation, and this one is the maximum evaporation that you can have based on unlimited water availability. Okay, so that's what we're talking about. Before we're going into more detail of that method, I just want to talk a little bit about evaporation so that you get an idea of how it works. Okay? And I will only talk about how it works over water surfaces, because the evapotranspiration bit is more complex to explain, but it works similar. It follows similar principles. Yeah? So what determines the rate of evaporation? Evaporation is a rate, it's a flux, it's a loss of water in terms of units of millimeters per day or millimeters per month. What determines that rate is a combination of two features. One is wind speed, and the other one is the actual water vapor pressure deficit in air. Okay, and I show that as a little bit of a sketch here, and it's the top. Okay, so you're dealing with air which is undersaturated in water vapor. Okay, so less than 100% relative humidity. And if you're above a water surface, then you always have a transition zone which is 100% saturated. So you have an air that is 100% saturated, and this is sort of feeds into the air above. Okay, so evaporation is the flux from the saturated zone into the undersaturated flow. And the process that provides the flux is the wind. Okay, so if you have the stronger the wind, the faster is this flux, or the higher is this flux, the larger is this evaporation rate. Okay, so you need both. You need to have wind and a vapor pressure deficit. If you're confused about the term pressure, it's about in air. If you think about gases in air, it's all about the partial pressure that they have. So you have a total pressure, and that total pressure is the sum of all the partial pressures of each gas. Okay, the partial pressure is a measure of the concentration of that gas within the air. So don't get confused by my use of the word pressure. You can substitute this with concentration if you like. However, so the key story here is no wind means no evaporation. Okay, and if you have no water vapor difference near the surface, you also get no evaporation. What it means is if your air is fully saturated in water vapor, it cannot take up more water vapor, and there will be zero evaporation. Okay, that's essentially how evaporation works. There's a little bit more to it, because the evaporation rate, involves a heat flux. It's called a latent heat flux, and it implies a cooling effect. Okay, you might have heard of this effect. It's called the wind chill effect. Okay, so if you have strong latent heat flux, strong evaporation, it cools down. Okay, it implies a cooling effect. Okay. Oh, so this is just an explanation how this evaporation process works. Okay, and it is independent of precipitation. Okay, so going back to now, how do we determine the water balance? Okay, we might be better called the surface water budget, if you like. So how we do that is we imagine that we have a bucket. Okay, that's why this methodology is called the bucket. Imagine you have a bucket which is filled with soil. Okay, so at the surface you have precipitation as a source of water, and you got evapotranspiration as a loss of water. Okay, so now if you have a surplus of water, it's about the balance. It's about P minus ET. So if you have more precipitation than ET, okay, then you have a surplus, a water surplus. Okay, so you have water recharging the soil moisture, filling your bucket. If it's fully saturated, you might get a surplus and a surface runoff, feeding into rivers, getting a surplus, feeding into rivers, surface runoff. Okay. If evapotranspiration exceeds precipitation, you have a water loss. And this leads to a withdrawal of moisture from your soil, and eventually, if there's no more moisture left, to a total deficit. Okay, absolutely dry conditions. Okay? And it all depends, apart from precipitation and evapotranspiration, the problem of now determining the surface water balance depends on your soil water holding capacity. You can also express this in terms of millimeters. How many millimeters of rainfall equivalent can your soil hold? Okay, and then you can work out some models, put the equations together, and derive the water surface budget. And I show you an example. Okay, here we go. The example. This is one example for Dallas. Okay, So it's a little bit more complex, since I would want to spend a little bit of time on discussing what this graph shows. The horizontal axis are the months of the year. January, February, March, through to January again. Okay, the reason why people use January again is to show that it's a seasonal cycle that repeats, but in this example you can see there is a subtle color change that means something. To illustrate this color change, that's why they have the January. So let's see what you have. There are different curves here, and the one curve, which is the green curve, okay, is the precipitation curve. So this one you get from a climograph. Okay, these are monthly mean precipitation data. So this is one piece of the information. And you can see that there is some variation in there for this. So this is for Dallas in Texas. Okay. So now you also have a curve which is potential evaporation. Okay, it's this curve. This is the maximum possible evaporation that you can get. It also includes transpiration. It's added here. It's just the maximum curves that you get. And you can see that it's much higher in over the summer months. This is northern hemisphere again, than it is during the winter time. And probably forget to mention that the maximum humidity that you can uptake in the air is actually a strong function of the temperature. So it's actually temperature has a big control on that potential evaporation. Plus, and I said that before, it's the wind speed. The wind, you need the wind as a medium to induce the evaporation. So, and if you just look at the key messages here, you look at times where you actually have an excess of precipitation, and that's you have a water surplus, and these are the blue regions. Water surplus starts in October, okay, and lasts until May. Okay, one part of that period is used to recharge the soil. Okay, until October to December, it's the light blue. Then the soil is saturated, and then you get a period when you have a surface runoff period from January to May. Okay. The other period is the one during June to September where you have a net water loss, more evapotranspiration than rainfall. Okay, and you again split it into two parts. One is you have a withdrawal of soil moisture, and then you get a time where you have no more. You have a deficit, no more soil moisture available here towards the end of the period. So water balance diagram is a representation of the seasonal cycle of monthly mean values of the surface water flux budget. It sounds a little bit complicated, but it gives you more information than the rainfall because you can see how distinct a wet season and a dry season can be. If you take into account for the evaporation and factors that influence evaporation. All right, I want to show you more examples. Okay, let's have a look at comparing Hong Kong with New Delhi. Okay, and this is the same example that I used to discuss and compare the climographs. And the climographs are shown here at the top. On the left is for Hong Kong, on the right is for New Delhi. Okay, and you can see it looks sort of, it's not much difference, isn't it? You can see, there's less rainfall. It's not as big, the rainfall over the summer months, and it starts later. Okay? If you now work out the water balance, surface water balances, you can see that there are significant differences. there are big differences. You know, you can see in Hong Kong you have a long period where you have a water surplus and even a runoff. There's all the blue areas here for most of the year until including September. And you only have a short period where you have a soil moisture withdrawal. Okay? No deficit or whatsoever. In New Delhi, it's totally different because the rain season starts later. You have a very long period where you have a total deficit, you know, a total deficit in the soil moisture. So very, very dry conditions until you get the rainfall. So these are extremely valuable to construct these type of water balance diagrams because it can really tell you something about droughts and periods and when does a period start and when does it end. And also, how does it change under global warming if you now compare different periods? Extremely important and relevant information. Okay, so try to understand these diagrams. So let's see what else comes in this lecture. I think I have a little bit more. Okay, let's take a deep breath and look at droughts. Okay, because droughts are related to soil. In particular, we call agriculture droughts, we refer them to shortages in soil moisture in the root zone during the cropping season because of a lack of precipitation. Okay, if you think in terms of droughts, you have to think about the soil moisture content. Okay, so soil characteristics is an important indicator of the climate of a region. Droughts are defined as extended periods of low moisture content, a low soil moisture content, and various indices are available to classify the drought condition of a region. The most popular index is the Palmer Drought Severity Index, PDSI. Okay, and it's based on precipitation and evapotranspiration data. And it's similar to what we've just discussed before. Okay. In addition, there's something called the Crop Moisture Index. It's an index of the relative dryness or wetness affecting water-sensitive economies. And it's based on shallow soil moisture anomalies. And there's also the Keach-Byram Drought Index used to evaluate forest fire potential. Also based on daily water balance, on these water balances and the degree of soil water depletion. So you can see that these indices are all, they all rely on surface water balances. Okay, I'll show you one example. How does it look like? Example of the PDSI, the Palmer Drought Severity Index, and this is for the south central Wisconsin area from 1895 to 2012. So we're having something like more than 110 years of data or reconstruction of these index. Okay? And I don't give you the formula to how to calculate it, but it's essentially an anomaly where you define one part, shown here as green, as moist and the other one as drought. Okay? Moist conditions, wet conditions, and severe drought conditions. Actually different stages of the drought. Some moderate drought, some severe and extreme. Okay? And let's have a look at it. You can see that there are sometimes 10 years where you have extreme moist. Sometimes you have up to 10 years where you have a drought. And this one you can see it sort of repeats. But in the more recent decades, say from 1980 or even earlier, you can see that there's a majority of wet conditions. You know, wet conditions seem to be dominant in this area of south central Wisconsin. That's interesting, isn't it? I mean, you can see some changes. You can infer some changes. And I have a little bit more information on that. It's actually how has this index changed over the last decades. So let's have a look at that information. Okay, it's the changes of this index, okay, since 1900 using this Palmer Drought Severity Index. Okay, and you can see regions where there has been no changes are marked in white, and where you have the biggest changes in terms of getting wetter up to a unit of 4 in terms of this index is there in blue, and drier you can see in red and orange. And the Wisconsin area is over here in North America, and you can see that that coincides with the wet region. So this region getting wetter, okay, and other areas you can see a dramatic drying of the area here of the, just north of the equator here in Central Africa. You can also see drought areas, identified drought areas in Australia, including the Perth region in this index. Okay, so these methodology is extremely important to infer changes in precipitation, essentially. This is what it comes down to. All right, some study questions. Explain different ways to measure climate or to characterize climate. How long is the longest land-based temperature data set? How do satellites derive surface temperatures? What is a climograph? What is a water balance diagram? Which physical conditions result in droughts? Why are drought indices useful? So thanks for tuning in. I hope that you enjoyed this lecture. If you have any comments, please drop an email. Okay, thank you.